This is Origin Stories, the Leakey Foundation podcast. I'm Meredith Johnson. Today, we have a very special episode with two curated stories from our friends at the Science Podcast. The Science Podcast is a weekly show from the journal Science and the American Association for the Advancement of Science. Each week on the Science Podcast, host Sarah Crespi explores the latest discoveries with researchers and news writers from around the world. You'll learn about everything from how scientists are battling stink bugs using samurai wasps, to peacock tail feathers' ability to emit laser light, and how anteaters have evolved at least 12 times. Sarah and the team at Science sent us two stories just for you. The first story is from producer Kevin McLean, who you might remember from his Origin Stories episode about capuchin monkeys that use stone tools. In this first segment from the Science Podcast, Kevin interviewed Ann Gibbons, a writer at Science magazine who specializes in stories about human evolution. Ann recently wrote a feature about discoveries in South Africa's Cradle of Humankind, where researchers found remains of Homo erectus and two other species of ancient hominins, suggesting all three coexisted at the same time in the same place.
Hi, Ann. Welcome back to the Science Podcast.
Thanks for having me.
We are so glad to have you back. I know we have a bunch of different ancestral characters all living together, and I want to get into them. But first, when did you first get wind of this story, and when did you start tracking it?
We have known for quite some time that different hominins probably overlapped in Africa early on, more than 2 million years ago. We know this from different fossil sites in East Africa and South Africa, but nailing it down has been really hard. Because when you find fossils in a layer of sediment, that layer can represent a day or two, or it can represent thousands of years or tens of thousands of years. So it's hard to prove it. But we've been getting whiffs from different places. Not only have fossils been found in the same layers roughly, but footprints were found in East Africa. So this story has been getting interesting. We're beginning to see this magical coexistence. And a couple of years ago at a meeting at Stony Brook University, I heard this paleoanthropologist, Jose Braga, talk about his work at this famous site of Cradle in the Cradle of Humankind, which is a historic site where people have been working for a long, long time. And he talked about finding fossils of baby Homo, early Homo erectus, and also fossils of baby Paranthropus in the same layer. And I thought, oh my goodness, they're right next to each other. And then as I looked into it, it wasn't just his site, it was another site nearby. And I thought, oh, I've got to get there. I've got to get there and I've got to see this for myself. Then I just waited until the different teams working at the different sites would be there at the same time.
Yeah, you actually got a chance to go and visit the sites. I know you've written a lot about some of the famous sites in East Africa, but had you ever been to any of these places in South Africa before?
Yeah, I had not been to South Africa and I've always wanted to go, which when I got there, I thought, why didn't I get here sooner? I can't believe I have not been to the Cradle of Humankind, which is, a storied place. South Africa is also the first place where a fossil of a member of the human family, a hominin, was found 100 years ago by Raymond Dart. Certainly the earliest members of the human family arose in East Africa, but South Africa has yielded incredibly important fossils that illuminate other times in human evolution. What I was really interested in was when the first members of our genus Homo erectus, start to appear around 2 million years ago. This is a species that is a key human ancestor that eventually starts to have a much bigger brain and a body plan more like ours. And just a few years ago, a team in South Africa that worked at a site called Drimmelen found Homo erectus dating to about 2 million years. They said that these were the earliest members of Homo erectus. That, to me, was a really interesting moment when our genus is beginning to evolve, so it begins to look more like us. But who else was around when that was happening? How did that influence it?
Can you give me a rundown of the different hominins that you were talking about in the story?
At Cradle and Drimmelen and another site called Swartkrans, researchers have found two different genera, different genus. We're not even talking different species. It's bigger than that. Early Homo, which is our genus, and also Paranthropus, which is it means beside man, Paranthropus in Latin. And Paranthropus was a hominin, it was an upright walking. These are all upright walking apes, really, which is what we are. They're upright walking hominins. They didn't really look like us. You wouldn't, as other researchers have said, you wouldn't really necessarily invite them to dinner. They're going to be hairy, small-brained, with brains not much bigger than an ape's, walking around on the landscape upright. They are living in this area together. Paranthropus is more robust. The first thing you would have noticed about it is this huge head, which seems disproportionate to its small body. So that's Paranthropus, much more robust jaws and skull. Early Homo, still with a brain about a third bigger than an ape's, not huge at this point, probably still quite small as well. And then you also have lingering, we think, with some overlap based on dates from another site, we think Australopithecus. Now, if you've heard of Lucy, her genus was Australopithecus. She lived about 3.1 million years ago in Ethiopia. There is another type of Australopithecus in South Africa that starts to appear at least 3 million years ago called Australopithecus africanus, maybe more than one species. There's a lot of debate about this. Australopithecus appears first in South Africa. That was what the Tong child was from the 1920s. And this beautiful skeleton called Littlefoot around 3 million years ago. So we've got these different forms, very different kinds of hominins, all living in an incredibly small area.
When I was reading your story, I loved seeing the portraits of the different hominins or, what we think they looked like. You can totally see exactly what you're talking about. Homo erectus it's our genus and it looks the most like us. And then you get that smaller Australopithecus, and then you've got that big head and jaw of Paranthropus. There's also a really nice map in the story to give a sense of the geography of the place. I was so surprised these sites are really not very far apart from each other.
So that's the magic of South Africa. What's really special about South Africa is that these fossil sites are in a little area we're calling today the Cradle of Humankind. Okay, it's a UNESCO World Heritage Site, which is roughly the size of the District of Columbia or, the Principality of Andorra, whatever's most familiar to you.
Yeah.
The actual cave sites I went to are even closer. So all these caves, the area is riddled with these caves where researchers are finding incredible diversity of hominins. At different times, but especially around 2 million years ago, we've got these different kinds that were all there. And the big riddle is, did they see each other? Did they coexist? We know they were there roughly at the same time. And some of the researchers I talked to all seem to think it's almost hard to believe that they couldn't have seen each other, given how many fossils are at so many different sites. But you can't absolutely prove that unless you find them intertwined or you have DNA to show that they mated. And we don't have DNA that early yet for hominins.
The thing that was also interesting to me is, you mentioned this, these aren't new research sites. People have been looking in these places for a while, but there's sort of new findings coming out of them. What happened that helped people kind of make so much progress recently?
Robert Broom found Kromdrai in the 1930s, 1938. He'd been working at Sterkfontein, and a schoolboy found some teeth at another site, and he realized they didn't come from there. And then he had the boy show him where he found them, and it turned out it was Kromdrai Farm, which is where we actually stayed and where Jose Braga is working today. He went there in 2002, and he started re-excavating some of the sites that had been looked at in the interim, found the old pits because there were old Coca-Cola cans in the pits. He was able to discover where exactly the older fossils were. A dozen years and didn't find a single hominin, was beginning to think about going to Mongolia to look for fossils instead, when one day, sitting in the sediments, a tooth fell from above in the wall where he was working, hit him on the thigh. And it turned out it was a tooth from early Homo. Then he found more fossils of this baby Homo. And a few months later, he found the Paranthropus. So he was in the same layer right next to it. So that was terribly exciting. Then more recently, he's found something that looks like a skull. It's a beautiful skull that may be from Australopithecus, all in the same area. That has started happening in the mid-2015, somewhere in there, 2014. Since then, people at Dribblin found new fossils. And in addition to finding new fossils, dating methods and other methods of analysis have gotten more sophisticated to help them look at the riddle of coexistence.
What are some of the methods that have improved? How have they helped this discovery process along?
One of the key methods was Robin Pickering, who's at the University of Cape Town, has been using uranium and lead dating, which is radiometric dating, to date the minerals in the layers, to date those layers precisely. And if she can find the layers above and below a fossil and feel pretty reliably that it's in the proper context, she can get a pretty good ballpark of dates. Then Andy Harries from La Trobe University can come in and date the reversals in the paleomagnetic field. She will give him a window of time, and he can figure out exactly and much more precisely when that layer was laid down. So those methods together, along with some other emerging methods, which are a little more controversial, have helped research begin to really get a better handle on dates. And the sites I'm writing about are all in about the 2 million year ballpark. Meanwhile, there are other methods. You can look at the isotopes in the teeth to look at diet. Because not only do we want to know if they were there at the same time, but you want to know, were they competing?
Yeah. What do we know about how they divided up the landscape and the food resources that were available?
What's really interesting is researchers have long thought, when you look at the anatomy of Paranthropus versus Homo, it's got this gigantic, humongous jaws and big, robust skull with a crest on top so the jaw muscles can attach up there. So researchers thought it must be eating a hard diet of nuts and difficult things to chew, tubers, things like that. And that was how it adapted. And meanwhile, maybe early Homo was using stone tools more and maybe eating more meat, a softer diet. However, it's not as simple as that. There was a new study by Jose Braga and his colleague, Dr. Balter, who looked at strontium isotopes, and other researchers have looked at other aspects of diet, and they see that Paranthropus actually had a broader diet than people thought. It wasn't quite such a specialist. Maybe that robust jaw was an adaptation for hard times. When there wasn't much food around, maybe that jaw helped it survive. Meanwhile, early Homo was quite a generalist, probably eating figs and plants too, but some more meat. At that point, it may be scavenging, not hunting a lot. We don't know, right? This is early days for butchering. We don't know if it's got fire and cooking yet. This is awfully early for that. That probably came in later. Australopithecus was also a generalist, eating a lot of plants and occasionally probably meat when it could. The other mystery in all this is that stone tools appear before this in East Africa, at least 2.7 million years ago, maybe as early as 3.3 million years ago, and sometimes found in association with Paranthropus, a different species. So this suggests that more than one of these types of hominins is already using stone tools to process their food or butcher, whatever they were doing. So diet may not be the key to why they are different. And so Jose and people at Drimolen, Gary Schwartz and others, have been looking especially at the infants. There are lots of infants at these sites, which is really, really interesting. But there are a lot more Paranthropus infants that have died and ended up in these sites than there are Homo in ratio to the adult fossils they find. And so the question is that real? Is there a lot more infant mortality in Paranthropus? If that's true, what is Paranthropus doing differently from early Homo that is leading to so many infants dying? We do know that all these hominins, Australopithecus, Paranthropus, and early Homo, are weaning their infants earlier than chimps wean theirs. Chimps nurse their infants for 4 years or so. So that means mothers can't have as many babies because if they're nursing one, they can't have another. And the infants are dependent for a long time. What's happening with these hominins is they're weaning their infants earlier. They can tell from the isotopes in their teeth and the marked growth lines. And so that's a strategy perhaps when there's lots of predation pressure, a lot of horrible predators, big saber-toothed tigers, all sorts of things were around. So maybe they're producing more babies faster. But somehow, early Homo babies may be surviving better. There's some interesting hypotheses out there that are not proven yet that are really interesting ideas. And that is that maybe Homo had a social strategy already. They're weaning maybe a little later. They haven't proven this yet, but they're seeing signs of this. And perhaps the social group was able to provision the mother longer, to help take care of the infants better, to escape predators, to survive longer on the landscape. We know eventually that Homo erectus and early Homo, somewhere in human evolution before Homo sapiens, we ended up developing a life history strategy where we took longer to grow up, where our children had a longer childhood, which allowed for more social learning. We had bigger brains and allowed for more social learning. So we were more successful as adults and more successful as parents, and more of our offspring survived. The big mystery is, when did that kick in? When did Homo do that? And Jose Braga and some others think maybe they'll get clues this early on at these sites. As Jose Braga says, these infants, as the babies in the cradle, that may offer a window into the emergence of a deeply human kind of cooperation and life history strategy.
What do we know about why this particular place is where all these hominins would have shown up?
There was water everywhere. So there was a beautiful valley with lush trees, fig trees, things to eat, places they could build their sleeping nests. And the caves nearby also had water in them. When you have a cave system, this karst system of the caves, there's lots of water. So in an otherwise arid landscape, probably they were following the water and it brought them into the area. They ranged beyond it. They were probably nomadic, as hunter-gatherers are today, moving across the landscape, but they would end up there probably in dry times, especially. Plus, this is where they were beautifully preserved. That's the other part of this. It's not just, they weren't just in the caves, but the caves are this karst system. They get buried. The water that's trickling in that draws them there also turns the sediments into almost like the cement-like breccia, and it covers the fossils in ways that preserves them beautifully. So you have an incredible graveyard, basically, preserving fossils there. The hominins were elsewhere on the landscape, but this is where they're beautifully preserved.
Could you maybe just zoom out a little bit and just talk about how does this potential coexistence story, how does it mesh or not mesh with what we've always sort of historically thought about human evolution?
So a long time ago, Ernst Mayr was a famous evolutionary biologist who proposed this notion that hominins, human evolution was special. We weren't like other apes, that there was one kind of hominin at a time evolving into another. And it was sort of this wonderful, straight, neat line of descent from early Australopithecus to early Homo to us. But even he started to disbelieve this probably in the 70s when we began to find, even in East Africa by then at Olduvai Gorge, researchers found Paranthropus and Homo near each other in similar sediments, roughly dated at the same time. So we began to realize we were not the only hominid on the landscape. But the question was that at the same time or not? And then I think the big breakthrough that has made a huge difference in people's understanding of human evolution has been with the ancient DNA revolution in the last 15 years. We found that we interbred with Neanderthals, as you said in the beginning, and also these other kinds of hominins called Denisovans. We have DNA from them as well. They were cousins of Neanderthals that lived in Asia. So we know that our ancestors, Homo sapiens, bred with anything else it could, the other hominin, and they actually had offspring that survived because we have this percentage of DNA. This suggested that this was a human strategy. And it's hard to believe that we didn't do this all through human evolution because all other apes do this. You've got interbreeding between different species of orangutans in the wild and in the zoos. You've got it between subspecies of chimpanzees, even though they have more genetic variation than we do as a species. I think most researchers think, yes, we did coexist with other hominins. We probably interbred, but how do you show that? How do you prove it? That's why these fossil sites are so interesting, because they're in such a small area of time and space. And so if there's any place that's promising for this, this is one of the sites.
Well, thank you so much, Ann. It's always so much fun to hear from you and hear how excited you are about these new findings.
It's the best beat of all, human evolution.
Ann Gibbons is a contributing correspondent at Science. You can find a link to the story we discussed at science.org/podcast.
The second story from the Science podcast is a conversation with anthropologist Melanie Beasley about a surprising and kind of gross new discovery about what Neanderthals ate. Every episode of their podcast has segments like this, interviewing scientists about their brand new research. It's a great way to stay informed about all kinds of fascinating science. Here's host Sarah Crespi.
Teeth and bones contain isotopes that tell us something about what someone ate during their lifetime. I first encountered this idea when talking with a researcher about the fall of the Wari people in Peru around 800 CE. Their bones told a tale of violence and limited food. The isotopic ratios in bones also place animals on different trophic levels. Are they eating mainly plants, mainly animals? Where on the food web are they? When this question was asked about Neanderthals, they read as hypercarnivores. Their isotope ratios made them look like lions, more meat intense than lions. But these cousins of ours have similar digestive systems to us. They're not like hyenas. Anthropologist Melanie Beasley wrote in Science Advances about another possible cause of these surprising numbers. Neanderthals could be eating fly larvae from putrefying meat. Hi, Melanie. Welcome to the Science Podcast.
Hi. Thank you so much for having me.
I think to get to the meat of this issue,
The meat of the issue.
we really need to talk about the isotopes, just kind of a quick overview of what isotopes we're looking at, what this number is, this level is, and then we'll kind of keep it simple from then on. But let's just dive into that real quick.
The easy way to think about isotopes is you are what you eat. And so all of the foods that you eat and consume, they have nitrogen and carbon, as well as other elements. But what we mainly focus on with diet is nitrogen and carbon. And when you look at this in the bone collagen, so the organic protein kind of component of your bone, That's what it's doing, is it's giving you an idea of what proteins are being consumed by whatever you're analyzing, be it a deer, be it a Neanderthal, modern human. And so the nitrogen comes in two different isotope forms. There's the heavy nitrogen, the N15. That's the very rare isotope form of nitrogen. And then there's the abundant light isotope, which is nitrogen 14. And so the delta N15 value that we're looking at is actually a ratio of N15 to N14 compared to a standard. And so all that we're looking at in these values is how much of that rare to abundant isotope is there. And it turns out during decomposition, as the body breaks down, then what you get is the light isotope will be the first isotope to react in these chemical reactions that are releasing these volatile compounds. And so that means that the muscle, the body, retains the heavier isotope compared to the light isotopes. You get this change in these isotope ratios of the heavy to the light isotope. And over time, as you continue to lose more of that light isotope faster, because that's reacting faster in that chemical reaction, you then get a higher and higher delta N15 value.
How does that link in with what you're eating? Like saying, you eat a lot of meat versus you are more of a herbivorous animal.
I work in California as a bioarchaeologist. And so I like to use the deer example where you have grass. That's going to have a starting nitrogen value. The deer eats the grass. That's going to have a trophic level offset. So a standard kind of value that is offset between the food that you're eating and the animal that is consuming it. And so that would be your herbivore value or your primary consumer. Then in the trophic food web, if a carnivore eats that deer, so say a wolf comes along, eats that deer, it's going to have that same offset, but now as that secondary consumer. So you're going to get an even higher value. And so what's interesting about the Neanderthals is when this first research was done in the 1990s, and they were extracting the bone collagen and able to isolate the nitrogen isotope values, what they originally found is that Neanderthals were at the top of the food web. They were above the carnivores. And that's where this narrative of hypercarnivory came from, is they've got nitrogen values above carnivores. They must be doing this as a hypercarnivore.
They must be eating tigers, whatever.
Exactly. But of course, that's not what they were consuming based on the bone remains that were at these sites. We knew they were eating herbivores. So it was always this question of like, okay, well, are they just eating more meat? Is that where this hypercarnivory is coming from?
Is that what bones were around? Is that what made you say this probably isn't right? This has to be some other reason for their nitrogen values to be where they're at?
The pushback that has always been there in thinking about these high nitrogen values is that we know that Neanderthals are a hominin. Hominins are primates. We have evolved as a primate digestive and metabolic system. And so we aren't designed evolutionarily to just be primarily eating flesh. We aren't a carnivore. So there are limits to that amount of protein that we can consume.
I thought this was so interesting. The idea that there is this almost like a hard limit. Like if you're eating more than 300 grams of meat a day, you're going to overwhelm your liver.
You are.
You're going to not be able to deal with all that nitrogen.
That's the amazing part, is this is known by these historic explorers. Like think about these explorers coming across North America. They would actually starve, what was referred to as rabbit starvation, because they would have all of the meat protein that they could eat, but they wouldn't have carbohydrates. They'd be hunting lean game meat, so they wouldn't be eating those fatty portions necessarily, and they would starve.
You talk about what indigenous populations were doing at that time, and they're like, why are you eating the leg muscles? We eat the fat and the brain. They went for the fatty stuff because they had figured out over time that you cannot just eat like this nitrogen rich, straight up amino acid.
Absolutely.
And survive.
We think about, Sunday roast for dinner. That's not what early hominins and prehistoric indigenous groups were doing. They were going for the fatty bits.
One other thing that came out of that historical perspective was that, and you have these quotes.
All collected and curated by John Speth, my co-author. He is an absolute bibliophile of collecting this just rich ethnohistoric quotes that span the world.
I would love it if you'd read one of the quotes from the paper.
Oh, I'll read the first one, the intro, because that's my absolute favorite. Okay. The meat was green with age, and when we made a cut in it, it was like the bursting of a boil. So full of great white maggots was it. To my horror, my companions scooped out handfuls of the crawling things and ate them with evident relish. I criticized their taste, but they said, not illogically, you yourself like caribou meat. And what are these maggots but live caribou meat? They taste just the same as the meat and are refreshing to the mouth.
It's not like it was only in hard times that they wanted this resource. This was something they actually, I wouldn't say cultivated, but it was not accidental that they encountered maggots.
That is correct. It's definitely not accidental. I actually tried to put the word cultivated in the paper.
Yeah, you're going to get in trouble.
My co-authors were like, that's pushing it a little far. You gotta rein that in. But in my mind, in Neanderthal, these prehistoric foraging groups, early anatomically modern humans, they would have quickly observed that these maggot masses would be associated with a butchered, decomposing carcass. So even if they hunted and took those choice pieces first, they might not have taken the entire carcass back with them to wherever they were storing or consuming the food. But I bet you that they were like, that carcass is there, and I'm going to come back in a week or two, and I'm going to be able to scoop up those fatty, tasty maggots and just get a quick, energetic treat by popping that in my mouth.
Do we have any evidence that they were storing meat for later?
I don't know that we have specific evidence of storage of meat. They were not eating meat like a carnivore was eating meat. They were doing something to it, storing it, cooking it, drying it, doing some sort of cultural processing of that food like humans do. And that is what we're seeing with these high trophic values that aren't what are expected. And of course, you can't prevent the flies from getting there, so you can't get away from those maggots. And so that is probably the maggots are getting in there. You're getting that additive food on that paleo menu, which is also raising the nitrogen value.
Yeah, let's get into that. The paper takes us a step in the direction of seeing if we can detect intentional maggot eating in Neanderthals. Step one, find out how much fly larvae might influence the nitrogen levels. You can do this by testing a tissue, then testing the putrefying tissue, and then testing the larva after they eat it. Before we go into those steps of your experiment, you used human tissue to do this. Can you talk a little bit about why you decided to do that?
It's really more of a story than anything else of everything aligning perfectly. John Speth was doing this research, his 2017 paper proposing putrid meat, and he came to give a talk at UC San Diego. And I went up to him afterwards and I was like, John, I'm applying to a postdoc at University of Tennessee to the Forensic Anthropology Center and do isotope experimental research. I could propose to them to look at the decomposing tissue and see what happens to the nitrogen values. And when I got there, I basically asked, I said, I have this idea and it has dual purpose because by doing it with human tissue at the Body Farm at the Forensic Anthropology Center in Tennessee, which is the world famous, known as the Body Farm, was started in the 1980s, that focuses on human decomposition research for doing forensic anthropology casework. I could say nobody's looked at this as an estimation of time since death. This could be a new method that we could use in forensic anthropology to estimate how long someone has been dead during that period of time that is often difficult to identify how long have they been actively decomposing. And so for me, it was using this real world applied anthropology, forensic casework related project that then I could take that same data and use it for this proposal of high nitrogen values in Neanderthals, because muscle tissue is muscle tissue.
So I was wondering if it was starting with the trophic level of people and then seeing if what the maggots did. But it sounds like that was not as important as having access and meat is meat and it had this dual purpose.
Exactly. And in the paper, I do talk about essentially if you adjusted what that starting substrate muscle level was for what we use in humans, but we adjusted that to just the average of the herbivore meat value, you still get nitrogen values that are of the fly larva that are astronomically higher than anything else that we see that would be being consumed. And to put this in perspective, when you think of high nitrogen value foods, we're thinking marine mammals, pinnipeds, consumption of seals.
That's just like this endlessly long chain of food. Like you're just at plankton and then like 7 kinds of fish. And then you finally get to something fatty like a pinniped, like a seal or a shark or whatever. That's just eaten the entire food web basically in one bite.
Absolutely. But even in those values, you're only getting into like the low 20 per mil kind of for at most. And these fly larvae go up to 43 per mil.
Oh my gosh.
It's astronomically high.
Right. And like a lion is like an 8, right?
It might be more like 8 to 10, somewhere in that
8
range.
to 10, right?
I'd have to look at the exact values for the averages.
So a lion is more like a 10. And then you have these sea eaters, they're like a 20. And then for some reason, the maggots eating putrefied flesh are 40. Does the putrefying flesh part make a difference? Does it matter if it's fresh tissue or putrefied tissue?
It does. It ups the number on orders of magnitude. So the black soldier flies, they arrived in June, and I sampled them from June until essentially December when I could no longer collect live fly larvae anymore. And that just trend increases and increases and increases. And so part of it is that the muscle is long gone, the tissue is long gone. But what has happened is through decomposition, that, let's say, soupy, decomp, fluid rich soil is what the flies are still attracted to. And those maggots are continuing to develop in that soupy, nutrient rich soil. That cycling of nitrogen is continuing. And though those maggot masses are still associated with a skeleton, they're not actually feeding on the fresh muscle tissue anymore. That's been gone for 6 months, 9 months. But that fly larva is still there in mass, like huge masses of fly larvae. It's incredible.
The idea then is that you can go back to a kill site and say, oh, there's not really much for me to chew on, but look who's been chewing on things for me. And I can now harvest that from the maggots.
Absolutely. The interesting thing too is like, if you think of lean game meat, the maggots are converting that lean game meat into a fatty additive, basically. So now you're getting a more nutritiously complete paleo menu item.
You looked at a number of different flies and their larvae over this period of time.
There are 3 species.
Do these guys coexist with Neanderthals? Like, were they around at the same time in the same place where these measurements were taken?
So we don't know specifically that the specific species of black soldier flies were around, but we do know that the family of flies were around at that time and had already evolved concurrently. And so there would have been flies. Flies would have been there and landing and interested in this animal stored foods.
And it wasn't too cold for them or anything like that, because you went all the way to December in Tennessee, which is pretty cold.
It is pretty cold. And actually, if you look at the temperatures in Tennessee and look at some of the experimental research that's been done in Neanderthal temperatures, there is overlap.
Okay. Let's talk a little bit about some of the alternative explanations here. Like, as we mentioned, like eating out of the sea can really boost nitrogen levels. Is it possible that Neanderthals somehow had access to a lot of fish, a lot of high trophic level sea critters, and that kind of, or termites? I don't know, something else. Like, how do we eliminate those other possibilities?
I don't think that we do. I think we need to reframe this focus on hypercarnivory and mammoth eating and eating so much meat. And we need to kind of try to change this narrative. And this narrative, there has been pushback on for the last 20 years, and yet it persists.
Oh, yeah. If we look at anatomically modern humans that were coexisting with Neanderthals at this time, what are their nitrogen isotope levels?
Exactly the same
as Neanderthals?
Of the published literature, and I included it in the paper, the mean values of nitrogen for Neanderthals and the mean values for anatomically modern humans are exactly the same.
So everybody was at the barbecue. Everyone was eating putrid meat with a side of maggots. Everybody.
Absolutely. And I think the push has been, when you look at the archaeological record, the associated zooarchaeological bony remains, anatomically modern humans are often associated with having their high nitrogen value explanation is eating freshwater fish, eating waterfowl, eating a wider diversity of food. So having a wider diet. Neanderthals, the focus has been on hypercarnivory because you get the terrestrial mammal bones at those sites. You don't see the fish. You don't see the waterfowl. And so that's where, even though they have the same values, this interpretation has diverged in these two different directions.
But you have the grand unifying theory of maggots.
Yes, I'm going to become known as Maggot Melanie. It's just going to be in my future. The alliteration is there.
That's really interesting. I had no idea that it was exactly the same. At the end of the day, we have data, but we don't know how to interpret it. Like, we have a test that we like to do, and it's giving us numbers, but we need a story. We need other things to kind of prop up. That happens all over science.
That's the thing, is when we're talking about a story of Neanderthals, we've talked about it in terms of exceptionalism and how different they are and why they're different. And I think maybe it's time that we really reframe who our cousins are. Are they even actually cousins, or are they just us? They're probably doing things like cooking, storing foods, processing foods in ways that the baseline nitrogen value of what they were eating is just like what modern humans were doing to their foods. And you end up with those higher nitrogen values that place humans at that top of that trophic food web.
I get like pretty squicked out by not individual bugs, but like any kind of, as you keep saying, masses of bugs. Like, I really get. Did you have like that kind of problem when you're doing your field work there?
No, I did not. But my background, I worked at a coroner's office. So
Okay.
being around death investigation, being around dead bodies in varied states of decomposition, that's very normal for me.
Thanks, Melanie. It's been really fun talking.
Yes, this has been wonderful. Thank you for having me on the podcast.
Melanie Beasley is an assistant professor of anthropology at Purdue University. You can find a link to the Science Advances paper we discussed at science.org/podcast.
Thanks to our friends at the Science Podcast for sharing these stories. If you want to stay up to date on a wide range of fascinating scientific topics, including human evolution, subscribe to the Science Podcast now. They release a new episode every week. Origin Stories is a project of the Leakey Foundation, a nonprofit dedicated to funding human origins research and sharing discoveries. We'd love it if you would support this show and the science we talk about. Go to leakeyfoundation.org/origin stories. Your donation will be matched, doubling your impact on science and education. Origin Stories is made possible by our listener supporters, and Jeanne Newman, Camilla and George Smith, the Ann and Gordon Getty Foundation, and the Joan and Arnold Travis Education Fund. We'll be back soon with another new episode. Thanks for listening.